Hello students. In our today's class, we would be studying about grouping of capacitors. So this is the third lesson in the capacitor series. In the first two lessons or in the first two videos, we have understood what a capacitor is, that it is an electrical device that stores electrical energy and provides electrical energy in a burst to the required circuit, and that is how it differs from a electrical cell. Then we understood in the first class, or we went to the definition, that capacitance of a capacitor is defined as charge stored per potential difference, charge upon potential difference. And we understood that a good capacitor would be one to which, even if you keep giving charge and if its potential does not increase significantly, obviously it would allow you to store more and more charge, and obviously that would be a good candidate to be used as a capacitor, right? So we understood these definitions in the first class, and we also understood that though in the definition capacitance is equal to Q by V, capacitance in reality neither depends on charge nor on potential difference. Rather, when a capacitor is created, when the device is created, its capacitance get fixed. So God, assigns that, okay, hey, once you are, formed, once your dimensions are fixed, and the medium between your two plates is defined, your capacitance is defined as C, right? So that capacitance depends only on two things. One is the dimensions, like we understood, and second thing is the medium between those two plates. And apart from that, it does not depend on anything else. And we saw the manifestation of this in all the different kinds of capacitor that we started with in the second class. We started with a theoretical, spherical capacitor, and we understood that capacitance of a spherical cell capacitor is C equals to 4 pi epsilon naught R. And if you see here also, it depends on the dimension and the medium and on nothing else, right? Similarly, we learned in the evolution of capacitor and in yesterday's video that capacitance of a parallel plate capacitor is epsilon naught A by D, where A is the area of each of the plate. So we normally take two plates, each of area A, and when the spacing between them is very very less, right? So that is called as a parallel plate capacitors. Two conductors of relatively large area, but separated by a small distance, right? So that forms a parallel plate capacitor, and we found out that capacitance equals to epsilon naught A by D. And we understood that how to solve the basic problem of that is manifested by your spherical capacitor. How do we evolve from spherical to your spherical cell, from spherical cell to parallel plate capacitor, and from parallel plate to cylindrical capacitor. And obviously in use there are even many more, like as we discussed, that it is not mandated that your parallel plate capacitors, both the plates must be rectangle. They could be two discs, right? Two discs separated by a small distance, they can form a parallel plate capacitor. Two triangular shape plates separated by a small distance, they can form a parallel plate capacitor. So that is what we studied in our yesterday's class. And we understood the energy stored in a capacitor as q square by 2c, and we saw that is also equivalent to half cv square and qv by 2. So these all theoretical understanding we already had in our first two classes, and today we are going to go to next step, whereby we will see the series and parallel grouping of capacitors, right? And before we go into series and parallel, if you ask me that, sir, why at all in the earth we need to group capacitors either in a series or parallel or howsoever, we do not do anything without a reason, right? So we are very what you say, selfish people. When we do something, there's an intent behind that. So what is the intent of either grouping capacitors in series or parallel? And the answer lies in the same problem that you found with your spherical capacitor. Our intent is to increase capacitance, right? So to increase capacitance, what did we do? From a spherical capacitor, we went to spherical cell. We brought the second leg that was infinite to a finite distance. With this, we achieved something. Then we tried a parallel plate capacitor. We tried, your cylindrical capacitor, all those things, right? So these are one way of handling that. So we were playing on this dimension factor, that how would I change the dimension so that my capacitance would increase, right? We can also play around the medium and increase the capacitor, which would be the subject matter of our next class, when we'll talk about the effect of dielectrics. And today what we are doing along with these dimensions, right? So in Hindi, we have a very famous proverb, right? That एक एक से भले दो, or दो से भले तीन. So rather than one person attacking the enemy, if I have more number of people and if I attack them with my army, obviously my chances of winning go high, right? So obviously what people started thinking that, hey, can I group capacitors in a particular geometry so that the effective capacitance would increase? So I repeat, the reason why we group capacitors either in series or parallel is we want to increase capacitance, or maybe in some places even decrease also. So let me not say only to increase, but predominantly we would do it to increase the capacitance, right? So let us understand what is series combination. Let us understand what is parallel combination, and we will go further from there. Okay. Now, before going into the theoretical definition of series and parallel, I would pause a moment and I would repeat the same theory that I taught you for series and parallel combinations of your registers, right? I taught you Rajiv's or my lover couples versus happy married couple theory, right? In registers, we had understood that if this is register R1 and this is register R2, I had said you that if at the meeting point or the junction point there are two and only two registers, then they are in series, right? Similarly, I have said you that in any geometry of a circuit, if you can complete one loop, this is R1, this is R2. Just take any two registers, and if you can complete one loop, then we say they are in parallel, right? So this is just like your two lover couples, that there must be only two people. The moment the third register R3 enters, their relationship goes for a toss. So now they would not be in series anymore, assuming that this is not open circuit, right? And similarly, in parallel case, they are like a happily married couple. So they have their own world defined. So they have sealed it from all the sides. So even if there is anyone else, it does not really impact their relationship. They can still continue their life happily, right? So the similar concept for problem solving. I repeat, do not write this in your exam, because obviously this would not fetch you marks. This is for understanding purpose. That if 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 at the meeting point, so this is how we normally represent capacitors in electric circuit. So this is suppose C1, this is C2, this is the meeting point. At the meeting point, if there are two and only two capacitors, I repeat, two and only two, then they would be said to be in series. So here I'll say C1 is in series with your C2, right? Assuming if there is one more capacitor here like this, right? Right? Now, and this is C3. Now you cannot say C1 and C2 are in series. because this is the meeting point, and at this meeting point there's a third capacitor C3, and that is creating the disturbance. So there, our relationship is in trouble. So in this case, now C1 is no more in series with C2, right? But here, if you see, there are two capacitors C3 and C2. By taking just these two, I can complete one loop, right? If I can complete one loop by taking two and only two capacitors, I can say that they are in parallel without any doubt. Okay. Now let us come to the theoretical definition of understanding series and parallel, and understand how do charge and potential difference get distributed when we connect capacitors in series and parallel. Okay, so let us start with series. Okay, so two capacitors are said to be in series when they are connected, end to end with each other in a way that charge across them is same, right? When two capacitors are sorry when two capacitors are connected in such a way, end to end, one end of this is connected to the other end of it, it's connected in such a way that charge across them are same, then they are said to be in series with each other. So this is our bookish definition. So suppose this is a cell which provides a potential difference of V. You have two capacitors C1 and C2. Charge across them is same. Then here we will say that C1 is in series with C2. Okay. Now this is the definition, but now let us also use our analytics, our analysis rather, to understand if two capacitors are connected like this, will charge actually remain same on them or not, right? So now the moment I connect this to an external potential difference V, what will happen? This is a metallic conductor, right? So so do we know that metal have abundance of electrons with them? They can provide as many electrons as needed, because they have a huge amount of free electrons with them, right? So the moment I connect a cell to it, obviously some n number of electrons would move from here to here, right? Again, as we studied yesterday, due to the effect of the cell, or due to, or what does cell do? Cell spends the chemical energy to push electrons from the positive terminal to the negative terminal. So the electrons now would come here. Once the electron reaches here, obviously negative would repel negative, so this electron would come and hit here. So if I, give them namings, right? So suppose this is plate 1, this is plate 2, this is plate 3, this is plate 4. So if one electron is coming out from plate 1, that same one electron would go and sit on plate 4. So if n into e electrons have come out of plate 1, then obviously the same any number of electrons would go and sit on plate 4, right? Now we know charge is quantized. So if n into e electrons have come out of plate 1, then obviously this one would have attended some charge plus q. If this has got charge plus q, what would be charge on plate 4? It will obviously be minus q, because the same Ne has got transferred, right? Now this is where, and after some time, when the potential difference across 1 and 4, when V14 becomes equals to V, then after that no more charge movement would be there, it will be stopped. And this happens very very quickly. Okay, now after that, what would happen? Okay, now this is a metal having charge q. I have placed another metallic surface at a small distance d, which I have indicated as 2. So obviously it will induce charge minus q on this, right? Similarly, this charge minus q would induce a charge plus q on this, right? Now, what is the charge on capacitor C1? What is the charge on capacitor C1? We say that when one plate of a capacitor is given charge plus q and another plate of the capacitor is given charge minus q, charge on the capacitor is called as q, right? So charge on C1 is also q, charge on C2 is also q. So obviously this is the understanding, or this is by analysis also we have established that when two capacitors are in series, then obviously charge across them would be same. Now you may ask me a question that, sir, here we have two capacitors, so that's why they came out to be in series, and then what you say, charge across them are same. Now suppose here I will connect one more capacitor, right? So say I will connect one more capacitor C3. In this scenario, what would happen? Let's see. So in this scenario also, if you see, it's no different. If charge any is coming from, if n into e number of electrons are coming out of one, those same any electrons will go and sit here. So if here it is plus q, then here it will be minus q. Here it is minus q, then here it will be plus q, right? So here it is plus q, here it will be minus q. If here this is minus q, now if you see between plates 2 and 3, right? Plates 2 and 3, two ways to understand it. They constitute, or they form an isolated conductor. If you see, these are two plates connected by a conductor, so they are just like your any material line anywhere, right? So obviously, if charge here is minus q, here charge has to be plus q, so that the net charge on this is zero. Because we know, as per the conservation of charge principle, the total amount of charge in an isolated, system is always zero. So obviously, charge here will be plus q. If here it is plus q, obviously, you can either say that the induced charge here will be minus q, or the other way of understanding, if you see, even this one is an isolated system. So in this isolated system also, if this is plus q, this will be minus q. So here also, charge on C1 equals to C2 equals to C3, that is equals to q. So that's why students, that let us understand that when capacitors are connected in series, charge across them you know is same, right? Now let us understand, if charge across them is same, then what else differs? Okay, so I will just clean out this slightly, so that it will be easier to understand. So let me redraw it, and let me redraw it just by taking two capacitors. So this is capacitor C1. Okay, the length should be same. This is capacitor C2. Okay, and they are connected in series against a potential difference V. Okay, now for the sake of understanding, let me give name to some of the points. A, B, suppose this is your C, this is point D, point E, point F, point G, and point H. Okay, and plates also, if I want, I can name them, right, like 1, 2, 3, and 4. Okay, now here if you see, what else would be changing. So we understood that charge on each of them. So if charge here is q, here it will be minus q, here it will again be plus q, here it will be minus q. So this much we have already understood. Okay, now let us see one more thing, right? So we know potential difference is always a point function, Like we have studied even in your gravitation also, and in electric field also, we have studied it so many times that potential is always a point function. So if this is point A, if this is point B, I go from point A to B in whatever path, the total work done, if I follow this path, or I follow this path, or I follow this path, total work done will always be same. If work done is same, and we are considering a conservative field, okay, just like your electric field or magnetic field, like talking about only a conservative field, okay, that the total work done will always be same. If total work done is same, and if potential is a point function, so can I say this thing that if I go, so when we are saying that a cell provides potential difference D, what does it mean? If I go from the negative terminal of this cell to the positive terminal of this cell, the potential difference would be how much? V. So can I say that if I go from B to A, so potential, I'm going from B to A, so potential VAB is nothing but B, right? I'm going from B to A. So the potential difference is nothing but V. Okay. Similarly, first I went through this path. Okay. Now I said no, no. I'm a very industrious person. I don't want to choose an easy path. I want to go through this longer looking path. Okay. So when I go from B to H, assume potential here was zero. Okay, if potential here was zero, right? So what would be potential at B? VB will also be zero, right? If VB is also VB is zero, can I say that your VH will also be zero, right? If VH is zero, can I say that your VG, this one will also be zero, because between here to here there is no other electrical device, and there is no change in potential difference, no current, no resistance, right, or no other electrical device. So Vg is also zero. Now between Vg, between point G and F, between point G and F, will there be any potential difference? Obviously, yes, because here you have charge plus Q, here you have charge minus Q, which means there will be an electric field from here to here in this direction. Some electric field E1 will be there. If there's an electric field, then obviously there's a potential difference, because we know E is nothing, E by D is nothing but your V, sorry, uh, yeah, v by d dv by dr is nothing but e. So if the spacing between them is very small as d, then if there's an electric field, or we can say it's your dv by dr. So if v equals to, if there is no v, then obviously your e cannot exist, right? So when I go from G to F, there would be some potential gain. Okay, so let us say that potential gain is V2. And why I'm saying potential gain? Because I'm going from the negative terminal of the capacitor to the positive terminal. If I'm going from -3 to +5, obviously I am getting a rise. So obviously potential is, gained. So that is why we are saying the potential gain would be V2, right? So obviously potential at point F till point F, it will be how much? It will be your V2, right? Now between point F and E, we have a conductor, right? So obviously, if there is any potential difference, then charge would have flown. So which means between here and here, there is no potential difference. So I can say that potential at point E, potential at point E, this will also be V2, right? Right? And this is compared to B, potential at E with respect to your B. This will also be V2. Now, when I am going from E to D, just like we understood here, there should be an electric field from here to here. And for that, there must be suppose one potential difference V1. So can I say that my VD with respect to B will be nothing but, see here we already had V2, so it will be V2 plus V1. After D, if I'm going to C, right? So potential of C and D are same. Similarly, potential of C and A are also same. So can I say that potential of A with respect to B is also V2 by V1? So this is one important thing. And if you see, we arrive at the same thing. Whether I'm going through the cell, potential was V. Whether I'm coming through this longer path, potential is V. So by taking this one and this two, can I say can I say that V here is nothing but V1 plus V2, right? Now we know the formula Q equals to CV. So can I say V equals to Q by C? Let us start putting it in this case, right? Now, it is very easy to put for V1 and V2. So for V1, what is the charge? Charge is Q by C1. For V2, it's nothing but Q by C2. Now, what would be the potential in terms of charge and capacitance for this one? So here comes the funda of series and parallel grouping. So we are saying that we have seen this as a combination. If we draw an equivalent circuit, suppose if I'm drawing an equivalent circuit, then I have only one capacitor connected with one cell, right? So, and we'll call this one's capacitance obviously will be CEQ. Charge would not be different, it will be Q only, and potential will also be the same, it will be V only. So, that is the fundamental of your effective capacitance. So, that's why we say this is the effective capacitance across these 2 points or these 2 points, whatever you want to say, right? So, the effective capacitance is called C equivalent. So, can I write that Q by C equivalent equals to Q by C1 plus Q by C2. Now, obviously, all those Q will get cancelled out. So, can I write 1 by C equivalent equals to 1 by C1 plus 1 by C2, right? Okay. So, obviously, this one you can take as equation number one. Equation number one. Now, let us quickly see couple of quick derivations based on this. So, can I say that 1 by C equivalent is nothing but LCM would be C1, C2. So, obviously, this would be C2 plus C1. So, if I want to find out CQ, I would just divide both the sides by 1. So, this will be 1 by C equivalent is equals to 1 by C2 plus C1 by C1 C2. So obviously that would result in C equivalent equals to, this will go to numerator, C1 C2 by C1 plus C2, right? Okay, so obviously, if two capacitors are in series, then the equivalence capacitance should be C1, C2 by C1 plus C2. And if you see, this is just opposite of your resistors. In resistors, when resistors were in parallel, your R equivalent was coming up to be R1, R2 by R1 plus R2. In capacitance, it's just opposite. Okay, so when capacitors are in series, the equivalent capacitance becomes C1 C2 by C1 plus C2. And obviously, if C1 equals to C2 equals to C, then obviously your C equivalent will be how much? C1, or here we are saying both are C, right? So C into C by C plus C, that is C square by 2C, that is nothing but C by 2, right? So if two capacitors of same capacity are connected in series, their equivalence capacitance becomes C by 2 or half of it. Similarly, we can extend this we can extend this to if there are n number of capacitors. If there are n number of capacitors all connected in series, then their C equivalent would be how much? Obviously, C by N, assuming capacitance of each one is C. And and we saw it for two capacitors. Now here, if you have three capacitors, then your V would have become V1 plus V2 plus V3 plus V4, whatever. So that's why we can say 1 by C equivalent is nothing but 1 by C1 plus 1 by C2 plus 1 by C3 dot 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 plus 1 by Cn when you have n number of capacitors connected in series. Okay, so if you want to just take a quick note, you can take a note, and in the meanwhile, let me clean up the board for our next derivation. Okay, I'm wiping it. Good. So let's keep moving. Now, so we have seen that 2 points. 2 points you may note down that when capacitors are in series, when capacitors when capacitors are in series, your charge remains same across all of them, and your potential gets divided. We are not saying equally divided, right? But it gets divided. How it gets divided? Let's see. Okay. Okay. So how it gets divided? Let's see. So can I say Q1 is nothing but, or sorry, your potential V1 is nothing but Q1 by C1. Okay. Now let me find the ratio of V1 to V. Okay. So can I say V1 is nothing but my Q1 by C1 divided by V is nothing but my Q1, my Q, because in series, so charge will be same, so that will be Q. So Q by C equivalent, right? So can I say, obviously your Q will get cancelled out from, okay, or will, okay, so 1 by C1, 1 by C1 into C equivalent by 1, because obviously this will go to numerator and this will come to denominator, right? So can I say what is the value of C equivalent? This is nothing but C1 C2 by C1 plus C2 into 1 by C1. So C1 gets cancelled. So can I say this is nothing but this is what V1 by V. V1 by V equals to C2 by C1 plus C2. So can I say V1 is nothing but C2 by C1 plus C2 into V, right? So this is your next equation, right? So if you see here, if V1 equals to V into C2 by C1 plus C2, obviously your V2 would be C1 by C1 plus C2 into V, right? So if you see here, potential gets divided in the reverse ratio of their capacitance, right? So when capacitors are connected in series, charge remains same, potential gets divided in in reverse ratio of their capacitance. Okay, so what does it mean? Let us see a very quick numerical. Obviously you will not get this kind of numerical in exam, but it's just to understand what we are saying here, right? So here I have a capacitor C1 equals to suppose your 2 microfarad, okay, and your C2 suppose equals to C2 equals to 4 microfarad, and they are connected across a cell. They are connected across a cell of 6 volt, right? So they are connected across a cell 6 volt. So if I ask you, tell me what will be the potential V1 on this and what will be potential V2 on this, you can find it out very quickly. So see, total potential is 6 volt. Okay, what is the total capacitance? Total capacitance is 2 plus 4, that is nothing but 6, right? So this one, so can I say that C2 is nothing but 2 times of C1, right? So which means this voltage would get divided in two variables, x and 2x, right? And the one which has got lesser capacitance, we saw in the reverse ratio, right? So the one which has got lesser capacitance, it will get twice the potential that this one is getting. So if this one would get potential 2 volt, this one would get potential 4 volt. Okay, so and obviously the summation of both of them would be equals to this, and this is a quick way of checking. So and this, the reason why we are seeing this is this would be handy when we go ahead to calculate your or when we go ahead and solve electrical circuits where symmetry is very important. So these small concepts would make you understand the base of symmetry which we would use further to solve some complex circuits. Okay, so just give me a moment, I need a bit of water. Just give me a moment, I'm back. Okay. Okay, so let's keep moving. Okay, so this is about the theory for series. Now let's move into the theory for parallel. Okay, and then we would go into practice problems. So looks like we may not cover all the practice problems in today's class in the interest of time. So we'll cover a few, and then rest we would probably park it for the next video. Okay. So now let us see capacitors in parallel. Okay, capacitors in parallel. Now, when we are saying capacitors in parallel, suppose this is capacitor C1 and I have another capacitor C2 and I have connected, suppose, both of them across a cell of potential difference V, right? So we know that the moment a capacitor is created, its capacitance is fixed. Now we want to find out, right? So I want to find out the equivalence capacitance. And what is equivalence capacitance? We know that equivalence capacitance would be if I remove these two things and if I just put one capacitor C equivalent, right? So what should be the value of this C equivalent, which is equivalent to this entire geometry? Here we are seeing just two in parallel. It could also be a complex geometry. So C equivalence means we are connecting across the same 2 points. Okay. So we will find out what is the value of C equivalent. Okay. C equivalent. Okay. So let us see. Here we'll also take the similar approach. Let us see what remains same and what gets divided, right? Now, just like in series, let us first understand the definition of parallel. Okay, so the definition of parallel says that if two capacitors are connected at their terminals in such a way that the potential difference across them is the same, then they are said to be in parallel. Right? I repeat that if two capacitors are connected, by taking their terminals together in such a way that the potential difference across them is the same, then those two capacitors are said to be in parallel. So I have taken two as an analogy or two as a starting point. There could be n number of capacitors whose starting and end points could be joined together. So those n number of capacitors would be said to be in parallel, right? And when their potential difference across them is same. Okay, and let us also understand by analysis that will potential difference across these be actually same or not. Okay, now we know. So for that, let us do our same old practice. Point A, point B. Okay, this is your point C, D. This is point E, F, G, H. Okay, and suppose I, J, K, L. Okay, and these are placed 1, 2, 3, and 4 capacitors C1 and C2. Right now, what is the potential difference across these 2 points AB? So for that, I can choose any path, right? We just rehearsed that. I repeat, and you should always understand this is that a potential difference is always and always and always a point function. And what is the reason? That is nothing but F dot ds, right? So it's a dot product of your force and displacement. And whether you follow this path or you follow this path or you follow this path, the displacement is initial to final the position vector, right? So it's as simple as that. So that is the fundamental reason why your potential or potential energy is always a point function and it is not a path function. So I can choose a path from B to A through this cell, right? So obviously your VAB will be equals to V. I am going from negative terminal of this cell to positive terminal. So obviously there will be a potential gain. I'll get a potential gain. If there's a potential gain, I'll say potential difference when I'm going from B to A, that is VAB, is nothing but plus V, right? Now, can I say that potential of D equals to potential of B because these two are connected through a wire and there's nothing else in between them. Similarly, can I say potential of A is equal to potential of C, right? If VD equals to VB and VA equals to VC, so can I say that VCD, VCD, this is also V, right? Across these 2 points. If I take these 2 points, X and Y, right? So similarly, your C and X will be at same potential. D and Y will also get the same potential. So can I say VXY? This will also be V, right? Obviously. Now, XY, between X and Y, I have taken this path, right? And I have found out that potential across XY, right, is nothing but V. So so this is my first path. If I take, your this one as a second path, I'll go from Y to X through this path, right? So in this path also, obviously I'm finding Vxy. So when we are going through capacitor C1, what is the potential difference? It is again V, right? If I'm going from Y to X through this second capacitor C2, am I also getting the same potential xy? Obviously yes. So that is why, remember students, that it is so eminent or so clear that potential difference across capacitors that are parallel or electrical devices that are parallel would always be the same, because of the reason that potential difference is always a point function. Potential difference is never a path function. So you choose this path or that path or that path, your potential difference continues to be the same. Okay, so that's why it proves that your potential difference will be same. Now let me clean it up so that we can do some derivations based on this. Okay. Okay, so here I have capacitance C1, here I have capacitance C2, both of them are connected parallel and connected to an external cell with potential difference V, right? And now I knew that potential across C1 will also be V, potential across C2 will also be V, right? So C2, V, and C1. This one we know, right? Now the next thing is, what is the third parameter? The third parameter is charge. So can I say that charge across these two are also same? May or may not be. Let us not, say without analysis. Okay. Now, let us understand that. Let us understand that we know Q equals to CV, right? So between C1 and C2, C1 and C2, for between C1 and C2, we know that V1 equals to V2 equals to V, right? But in this scenario, C1 is not equals to C2. If C1 and C2 are equal, then it's a special case, and I would have written, C rather than saying C1 and C2. So obviously, if C1 and C2 are not same, then obviously your C1V will not be equals to C2V, right? So which means it would your charge across plate Q1 would not be equals to Q2. Again, would not necessarily be. If C1 and C2 are also same, then obviously charge will also be same, right? So we are not saying that they will never be equal. Most of the times they are not equal, given C1 and C2 are not equal. If C1 and C2 are equal, obviously charge will also be equal. Okay. Now, now, so can I say that charge across this is Q1 and charge across this is Q2. So which means the cell would have suppose drawn some n1 number of electrons from here, right? And those n1 number of electrons, it would have just pushed here n1e. So obviously that is why there will be a positive charge Q2 and a negative charge minus Q2 here, right? Similarly, there will be a positive charge plus Q1 and a negative charge minus Q1 here. So that's why we say charge on this is Q1 and charge on this is Q2. Now, as per our conservation of charge theory, can I say that total charge Q is nothing but Q1 plus Q2? Now, just let us start putting the formula. So Q equals to, I can say, Q is CV, so C equivalent into potential V equals to Q1. Q1 is nothing but C1 into V plus Q2 is nothing but C2 into V. Why V? Because we saw potential across all of them are same. So V gets cancelled. So it comes out to be C equivalent equals to C1 plus C2. Your next equation. So if you see, this is just opposite of your resistor circuit. Okay, so when resistors are in series, you are finding R equivalent equals to R1 plus R2. When capacitors are in parallel, you are finding C equivalent equals to C1 plus C2. Similarly, when resistors were in parallel, you are finding 1 by Req equals to 1 by R1 plus 1 by R2. And here, when capacitors are in series, you found out 1 by C equivalence equals to 1 by C1 plus 1 by C2, right? So now, just like we extended the equations for series, let us extend the equations for parallel, right? So suppose if your C1 equals to C2, if C1 equals to C2 equals to C, then obviously your C equivalent would be C plus C, that is nothing but 2C, equation number 10. Okay, if you have n number of capacitors in series, then C equivalent would be C1 plus C2 plus C3 up to Cn. And if all of them are same, then C equivalent would be N into C, right? Very simple. No rocket science here, right? So this is about capacitors in parallel, right? Now, one more thing. Just like we saw that when capacitors are in series, potential difference gets divided in the reverse ratio of capacitance. Now let us see how charge gets divided when capacitors are connected in parallel. So we saw when capacitors are connected in series, potential difference gets divided. When capacitors are in parallel, charge gets divided. So let's see that what is charge on the first capacitor. Charge on first capacitor Q1 is nothing but C1 V, right? So let me find out the ratio of charge on one capacitor by the net charge Q, right? So it will be nothing but C1 V by by C equivalent into V. So C1 V is nothing but C1 into V, no change. What is the value of C equivalent? It is C1 plus C2 into V cancels out. So that comes out to be your Q1 by Q, your Q1 by Q equals to C1 by C1 plus C2, or I can say Q1 equals to C1 by C1 plus C2 into Q, equation number 10. So that is why, obviously, if you see, your Q2 will be C2 by C1 plus C2. So if equation number 11. So if you see, charge gets divided in the ratio of capacitor. So if this capacitor is C, this capacitor is 2, capacitance is 2C, they are connected in parallels, and suppose I am saying that this cell provides your 9 coulomb charge to it. So if it provides 9 coulomb charge to it, obviously your 6 coulomb would come through the 6 coulomb would be appearing across the plates of this capacitor, and 3 coulomb would appear against the plates of this capacitor. This is what it means, that when capacitors are in parallel, charge gets divided in the ratio of capacitors, and when capacitors are in series, the potential gets divided in the reverse ratio of the capacitor. And if you see, that is logical also. Why? Because very simple, your Q equals to CV. Just analyze this and apply your analysis so that you would be able to find out that how this is logical. And I give it as a food for thought for you. Go ahead, think in home that why this is logical in light of this very simple theory. Okay. Now, let us get into practice problems. Okay. So I think we will be covering some practice problems today. Maybe we will have one more class on practice problems so that we cover a lot of them. Okay. So practice problems. Let's start. Okay. And for practice problems, I would predominantly use first my theory, because using that we can solve series and parallel very quickly. Okay. And I got one or two interesting circuits from HC Verma, so we'll go through those ones also. Okay. And then obviously some standard ones. Okay. So say this is my circuit. Okay. I'm creating a circuit like this. Okay. 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 Fair enough. And I'm asking, give me the equivalence capacitance. Okay. This is question number 1. Okay. And assume everything is C. Okay. For simplicity of calculation. C. Okay. If everything is C, what would be the C equivalent in this circuit? So let us quickly solve them. And for identifying, let me just give them some nomenclature. 1, 2, 3, 4. That's it. We have just 4 capacitors here. Okay, and points are A, B. Let me also give these 2 points as name P and Q. Okay. Now if you see, let us start solving. So I said I have 2 rules. If there are only two, connected at a point, then they are a happy lovers couple. If there is the third one, they are in not series. And if I can complete a loop, they are happily married couple, so they will be in parallel. Now, if you see between 1 and 3, if I take 1 and 3, can I say that 1 is in series with 3? 1 is in series with 3? Answer is no, because this is the junction point, and at this junction point, my circuit is still there, which means there could be some electrical device or something else connected. So which means I have a live part of the circuit disturbing at this point, at this junction point. So obviously, 1 is not in series with 3. Okay, is 1 parallel with 3? Let us see. I start from 1. Okay, let me start from 1. If I go from 1 to 3, I should be able to complete a loop, right? So let me start from 1. So I can say this is the starting point of 1. I started from here, I came here, I came here. So this is where the area of 3, capacitor number 3 ends, right? So just by taking 1 and 3, I cannot complete a loop also. So obviously 1 and 3 are not in parallel also. Okay. Now let me see if it is possible with others. Let us see between 1 and 2. Yes. 1 and 2 they are meeting at point P. And if you see there is no other disturbance. So in this case, I can say that yes, 1 and 3 are happy lovers couple, and these lover couples are in series. So one is in series with two. If one is in series with two, so this is C, this is C. What will be the equivalence capacitance? So equivalence capacitance would be C by 2. Now, if equivalence capacitance is C by 2, very simple. I would remove both of them. And in their place, I will just connect a capacitor of capacitance. How much? C by 2, right? Now, let us see this C by 2 and 3. C by 2 and 3, are they in series? This is the meeting point. Again, no, for the same reason that this is a part of a live circuit. Okay. Now, this C by 2 and 3, are they in series from this side also? No, because here also there is a disturbance, so they are not in series. But if you see, let me start from C2. I started from C2. I completed C3. So obviously this is also area of C2. So just by taking this C by 2 and 3, I can complete one loop. So if I can complete one loop, obviously they are a happy married couple, right? So even if there's anything else, they are still in parallel. So I can say that this C by 2 is in parallel with 3. If they are in parallel, then equivalence capacitance would be the summation of them, C by 2 plus C, that is nothing but 3C by 2. So obviously now I can remove both of them, and what I can do, in their place, I'll just put one simple capacitor, that is how much? Your 3C by 2. Now, this 3C by 2 and this capacitor number 4, are they in series? Obviously, yes. Don't think that series will always look like this. Okay? If this is an electrical, your limb of an electrical circuit, and this is a limb of an electrical circuit, if these points are AB and these points are AB, they are practically same. So whether you represent in straight line, vertical, or you twist it like this, or rather than doing it like this, if you make what you say, a shape like this, still this and this are in series, right? So this 3C by 2 is in series with C. So obviously I can say this 3C by 2 in series with C. So obviously their equivalence capacitance will be how much? 3C by 2 into C by 3C by 2 plus C1 C2 by C1 plus C2. Just find out what is the value. So the value is, in numerator we are getting 3C square by 2, and in denominator we are getting, 2 is the LCM, this is 3C, this is plus 2C. So these two cancels out. So your 3C squared by 5C, 1C cancels out. So answer is 3 by 5C. So this is your answer. Okay. So obviously when you are solving it in your entrance exam, it doesn't take this much of time. We just quickly say it, right? That you have one here, you have one here, this is the one, sorry, this is a capacitor, and this is another capacitor. These two are in series, so this is C by 2, C by 2, and this is C, so 3C by 2. So this 3C by 2 is in parallel with this, sorry, this 3C by 2 in series with this, and we quickly do a multiplication. So just in few seconds, you can solve this this equivalence capacitance of this circuit. Okay. Now let us go to the next one. Okay. Let us go to the next one. So I think as we have just clocked 1 hour, so I would have the relatively complex circuits where we will use your loop law and all in the next class. But we would see some more interesting ones, where we would play around geometry here. Okay, so let us go with a second one. Okay, so here, yeah, so. Uh, Suppose I have your letter A, I have two capacitors like this, there, more capacitor, more capacitor. I want to find out equivalence capacitance across AB. And here, this one is your, everything is C. Okay, so what will be equivalence capacitance? Obviously, if equivalence capacitance is would be nothing but C by 4. So these all are in series. Okay, so as I said, whether you are putting it all in straight line, don't think that only when they are in straight line they are in series. So if you see between 1 and 2 at this junction point, there is no third disturbance. Between this and this is the junction point, there is no disturbance. This and this is junction point, there is no disturbance. So all of them are in series. So C by 4 answer very quickly, right? So this is just your illusion. Okay. Now let us do some fun here. So I would put one more capacitor here. Okay. Now, if I'm putting a capacitor here, and now let me give them numbering 1, 2, 3, 4, and 5. If I give them these numberings, so if you see, first your 1 is in series with 2. So this is the junction point, there is no disturbance. So obviously they are a happy lovers couple. So 1 is in series with 2. So obviously the equivalence capacitance would be C by 2. So I'll remove these two, and in this place I'll put just one C by 2. This C by 2 is in parallel with this C. So C by 2 is in parallel with capacitor number 3. So it will be nothing but C by 2, and other one is C. So obviously C by 2 into C by 2 plus C, right? So this is nothing but C square by 2 by 3C by 2. So that is nothing but your 2 gets cancelled. So this is C by 3. Okay, by 3C, correct. Yeah. So C by 3. Now this C by 3, this one, and this one, they are all in series. So 1 by C equivalent would be nothing but would be nothing but how much? Your 1 by C plus 1 by C plus your 3 by C. So C goes LCM. So this is nothing but 1 plus C, so it is 5 by C, or your 1 by C equivalent is 5 by C. So this is nothing but C equivalent would be C by 5. Okay, so this would be the answer. So similarly, that would be many things that will play around. So let us just see a Wheatstone bridge, and we would stop after that, and from there we would resume in our next class. So let us go to our last practice problem for today, that is on Wheatstone bridge. Okay, so suppose I have one capacitor here, one more capacitor here, one more capacitor here, one more capacitor here, and one more capacitor here, such that this is C1, this is C2, this is C3, this is C4, okay, and this is any capacitance C5. They are connected across an external potential difference V. And here, if we are asked to find out the equivalence capacitance, obviously your series parallel will fail. Okay, so when your series parallel fails, then we should start looking for simplifying this circuit. And one of the first thing is you should look for, is there a balanced Wheatstone bridge? So this combination we know is called as the balanced Wheatstone bridge, and we have solved it in our resistances also. And we know it will be balanced when C1 by C2 equals to C3 by C4, similar to the resistors. When R1 by R2 equals to R3 by R4, so we are saying that this Wheatstone bridge is balanced. And in that scenario, we were able to remove the central limb. Okay, so for example, if suppose this is C, this is your 3C, okay, and this is suppose your 2C, this, oh sorry, this is your 2C, and this is 6C, right? So this by this is 3, is 1 by 3, this by this is also 1 by 3. So obviously this means it's a balanced Wheatstone bridge. So in that scenario, I can remove the central limb. If I remove the central limb, now these two are in series because this is the junction point and there is no disturbance. So obviously this will be your 3C squared by 4C. So C gets cancelled. This is 3C by 4. This part. Similarly, this will also be your 12C squared by 8C. C gets cancelled. This is your 2. Sorry. Yeah, 2, and this is 3. So this is again your 3C by 2. Okay, 3C by 2. Now, obviously, these two are in parallel, so you can add both of them, and whatever is the mathematical addition, that becomes your equivalence capacitance, right? So this is how you can solve it easily. However, suppose this is C, this is 3C, okay? And suppose this one is 6C and this one is 2C, and this capacitance is suppose uh, your 5C. In such a case, so this will be our practice problem number 4, which we will see in length in our next class. This one plus, so here if you see, this by this is not equals to this by this. It's in the reverse ratio, okay? So we will see how we will solve this and some more electrical circuits in the next class. So stay tuned. Our next class will also be on practice problems on electrical circuit. So and keep watching the my YouTube channel, and you would be getting the notifications for that. Thank you, students. You have a good time. See you soon with the next video. Thank you.